An X1.9 flare means Earth's GOES satellites measured the sun's X-ray output, spiking to about 1.9910 to 4 W amplitude from 150 million kilometers away. And the first hit arrives in just 8 minutes 20 seconds. So is that a real megafire apocalypse or internet panic? Stay with me here, because the difference comes down to one missing detail that most headlines never mention. Here's the mind-bender. Solar flares can dump roughly 2024 1026 joules of energy, depending on the event, in minutes, by snapping magnetic fields in the sun's atmosphere. If Earth released energy like that, you'd call it civilization ending. And the weirdest part is how the attack works. The flash hits before anything physical arrives. X-rays and ultraviolet slam Earth first, instantly changing our upper atmosphere. While the real geomagnetic trouble, if it happens, often arrives 1 to 3 days later, or sometimes not at all. Even worse, for your intuition, a smaller flare can cause a worse storm than a bigger flare if it launches the right kind of CME. Scientists around the world track this with GOES, SDO, SOHO, DS-COVAR, and more, and they still get surprised. So, when an X1.9 happens, what are we actually supposed to fear? To make sense of it, you need the normal rules. The sun is plasma, and plasma follows magnetic fields. Those fields emerge through the sun's surface and form giant loops in the corona. The sun's surface flows twist and shear those loops like rubber bands, storing energy in the magnetic field. When the stress becomes too high, the field lines suddenly reconnect, snapping into a simpler configuration and releasing energy into intense X-rays and UV, superhot plasma, and accelerated particles. That sudden release is a solar flare. NOAA's GOES satellites classify flares by peak X-ray flux in the 180 band. A, B, C, M, X. Each letter step is 10x. X means you're in the biggest category. X1.9 simply means 1.9 times the X1 threshold in that band. It's not a magic apocalypse code, it's a brightness measurement. This is where things get strange. Because the flare number mostly tells you about the flash, the radiation hit that arrives in minutes and can trigger shortwave HF radio issues on the sunlit side. But the long-term danger usually depends on what may follow. A coronal mass ejection, a CME, a huge cloud of magnetized plasma launched into space. If there's no CME, the story might end after the radio effects. If there is a CME, the clock switches from minutes to days. We learned that the hard way. 1859, the Carrington event sparked telegraph systems and drove auroras unusually far from the poles. 1989, Quebec suffered a major blackout after geomagnetic currents stressed the grid. 2003, the Halloween storms hammered satellites, radio, and navigation. Pattern interrupt. None of these begin with X-class alone. They begin with magnetized plasma arriving at Earth with the wrong magnetic orientation. That's why, the moment an X1.9 erupts, the monitoring chain lights up. GOES flags the X-ray spike. SDO shows the flare site in extreme UV and magnetic maps. Coronagraphs like SOHO watch for a CME bubble lifting off. Then everyone asks the suspense question: did the sun throw a CME toward Earth, or was it just a flash? And here's the cliffhanger. Even if a CME launches, the difference between pretty auroras and power grid stress can come down to one invisible parameter: its magnetic orientation, especially the north-south component called BZ. And you can't fully confirm that from the sun. So here's the 3-question countdown that explains what X1.9 really means. First, what happens immediately? In about 8 minutes, X-rays and EUV increase ionization in the upper atmosphere and can cause radio blackouts on the day side. NOAA rates these on the R scale, R1, R5. The flare label is most directly tied to this fast radiation effect. Second, did it launch a CME? And is it Earth-directed? This is the payload. A CME typically arrives in 1 to 3 days, sometimes faster in extreme cases, but direction decides whether it hits at all. Third, and this is the make or break, when it arrives, what is the magnetic orientation? If the CME's field is strongly southward, negative BZ, it couples efficiently with Earth's magnetosphere and can drive stronger geomagnetic storms. No AAG scale, G1, G5. If it's northward, Earth can shrug off a lot of the energy. Think of it like this. The flare is a camera flash. The CME is a battering ram. And BZ is whether the ram hits the gate at its weak hinge or glances off reinforced steel. That's why apocalypse isn't contained inside the label X1.9. The label is just the start of a checklist. And here's the uncomfortable truth. We can estimate CME speed and direction fairly early. But we often can't confirm the crucial magnetic orientation until the solar wind is measured close to Earth, by spacecraft near L1 like DSCOVR, often only 30 to 60 minutes before impact. That's why forecasts can feel uncertain right up until the moment they become very clear. Just when you think you understand it, the sun pulls a twist. Some X-class flares are confined, huge radiation, but no major CME escapes, so it's disruptive but short-lived. Some CMEs launch but miss Earth, or deliver only a glancing blow. And the nastiest storms can come from CME sequences, where a later CME plows through earlier solar wind, speeding up and reshaping the magnetic structure. Two events both labeled X1.9 can produce totally different outcomes because the label doesn't encode direction, internal magnetic twist, or BZ. So is it apocalypse or hoax? Neither. X1.9 is a real measurement, and the real risk depends on what comes after it. And this affects all of us. Space weather can reroute polar flights, degrade GPS timing that telecom and finance networks rely on, increase satellite drag, damage electronics, raise radiation exposure for astronauts, and stress power grids through geomagnetically induced currents. It also ties into fundamental physics, magnetic reconnection, and plasma turbulence, the same processes studied in fusion research and seen across the universe. The hopeful part? We're not helpless. We monitor the sun 24/7, issue alerts, and have mitigation playbooks. Satellites can go safe mode, airlines can reroute, grid operators can manage load. And the science is getting better. Missions like Parker Solar Probe and Solar Orbiter are sampling the solar environment closer than ever, feeding models that improve warnings. But this isn't the only sun threat. Next, we'll break down flare versus CME in one clean graphic, why auroras explode during storms, and what a modern Carrington-level event could mean for today's internet and power grids. Thanks for watching. X1.9 isn't a doomsday label, it's a measurement, and the real story is what comes after it. Keep looking up, keep asking better questions. See you in the next one.